All right, let's go ahead and get started. Couple things that I really need to remind you of before we get going. So, again, test is Monday. Basically, you'll have the entire class period to do it. So, as soon as 1 o'clock hits, I'll pass them out. You'll have the entire time. In preparation for that, let me get out of here. Don't lie to me. Oh, that's right. Math.asu did. The vast majority of math classes at ASU have their own website, including this one. So math.asu.edu/MAT242. So these practice tests here, like if you open up this test one, I think it's basically every test one that's ever happened, because your first test is not going to be 24 pages long, but this document is 24 pages long. Keep in mind, though, that I'm guessing that as this course has evolved, like the things that have been covered from test to test have changed. I have never mentioned Kramer's rule to you, so don't worry about that. At some point, this was a test one topic. It's not anymore. But like question 2 here, if I give you a matrix and ask you how many solutions it has, that kind of stuff should be fair game. If I tell you to find the inverse of a matrix by hand, that's something I should be able to expect you to do. So lots and lots of good practice in here. Keep this website bookmarked for the entire course, and then whatever math classes you take, pretty much every math class has a website like this where old syllabuses and old tests, things like that, get kept. Any questions there? All right. Also, the first thing I assigned to y'all was that survey, that Canvas survey. I responded to all those if you want to go take a look, but yeah, just go back and revisit that assignment, and all my responses are in there. All right, so we got a couple more things to cover before I declare you all ready for the test. So let's get back into it. So we were talking about finding determinants of larger matrices, and really the only straightforward way we have to find determinants is for a 2x2 matrix. So if we have a larger square matrix, we need to use this method called expansion by minors. So the two ways I've written down here to do this is only a partial list. So what's varying in each one of these lines is, actually, these aren't complete. So I'm keeping this I constant, and I'm counting from 1 up through n. So what am I varying in that first equation? Columns. So basically, I'm choosing a row and basically stepping through the column. Or you can choose a column and step through every row in that column. Either one of those is fine for finding the determinant. We did an example of that at the very end of class with a larger matrix, a 4x4. All right, so just resetting the stage. That's what we've been doing. That's kind of the big idea from this section. So we found, oh, we did this already. Did we do this? Okay, I think this is the very last thing we did. I'm pretty sure we did. Does anyone remember what it was? I feel like it was -40. Let's cheat and be absolutely sure. Because my memory is telling me that it was -40. And while I'm doing this, I should remind you the test on Monday is no calculator. As I cheat. Okay, -40. All right. So this determinant is -40, but if we remember back, how many determinants did we actually have to find? Was it 3? Okay, it was something. I thought it was 2, but again, we're going off of memory. But remember, what did we choose to expand on? Row 3. So that's one of the many very good choices to make here because all but one of the entries is non-zero. So if we expand off that, then we have to make a minor matrix, which the first minor you make is just going to be one row less, one column less than this. So yeah, I think the fact that there's so many zero entries here basically takes a lot of the work away, as opposed to where's the first one I had you do? This one here, I think we had to do everything, right? We had to really find 3 determinants of 3 minors. So now that we've kind of reminded ourselves of that determinant, how would I find this? Any ideas? What's the difference? Yeah, so what does it mean to square a matrix? Multiply it by itself. So I could multiply this by itself. Do we know how to multiply matrices by each other? And then once I did that, what would I have to do? So after I multiply these 2 matrices together, is the result still going to be something square? So this thing is 4 by 4, or being they're both 4 by 4, right? So how big will the product be? Also 4 by 4. So remember the dimensions come from these outer values, the number of rows of the left matrix and the number of columns of the right matrix, provided that these 2 entries or these 2 values are identical. So yeah, I can multiply these 2 things together and get a 4 by 4 matrix. Then what would I have to do with that? Find its determinant by expanding and finding minors again, right? Seems like a lot of work. I just wish there was some way to shortcut that a little bit. And there is. So here's something we can rely on. If I want to take the determinant of a product of 2 matrices, that's the same as the product of the determinant of the product is equal to the product of the determinants. So that's something we can take for granted. If we multiply a matrix by a scalar, its determinant is k raised to the power of n. What's n represent here? N is not the scalar, k is the scalar. N is number of columns, number of rows. So remember, when we're talking about determinants, what kinds of matrices have determinants? Only square ones. So A and B have to be n by n. So raise k to the power of whatever one of the dimensions is, rows or columns. The determinant of a transpose is the same as whatever it was. So why is that? So if here's a generic square matrix, basically with the transpose, I'm going to reflect everything over this diagonal, right? Which means anything I multiply along this diagonal is not going to change. What's going to happen to the things along this diagonal? Basically, this one's going to go here. This one's going to go here, and so on. I'm still multiplying them. I'm still multiplying the same pairs of numbers. So transposing a matrix doesn't change its determinant. The determinant of the inverse is the reciprocal of the determinant most of the time, unless your determinant is 0. So yeah, a lot of these things you can kind of take for granted without having to basically find a brand new product or actually do the scalar multiplication and then find a new determinant, things like that. So now that we know that, what can I say about this? The determinant of a squared should be equal to the determinant of a times the determinant of a, which is what, negative 40 squared? I'd rather do that than find the product of a 4x4 matrix and another 4x4 matrix. Because we have no reason to believe that that product would have all the zeros that this one does. So the expansion problem is probably a lot more involved. How are we doing? All right. So I got a matrix with some constants, some unknowns, and I want to know when this thing is invertible. So what does it mean for a matrix to be invertible?
The determinant doesn't equal 0.
The determinant is anything but 0. So basically, we want to choose values of x that are going to avoid that occurrence. All right. So that's what we have to do. Where should I go next?
Take the determinant.
Take the determinant. How do we do that for a matrix of this order? Pick a row or a column. Doesn't matter which row or column you choose. Right. Yes? I don't think it would cancel out the x's. Some of them. Let's try it. Let's try expanding by the column in the middle. Is that not what you meant?
Well,
okay. So, I mean, I said to you yesterday that it does not matter. So let's make a liar out of me. So if I expand off of column 2, then what minors do I need to make? So I think I'm going to need 3 of them. Row 1, column 2. Row 2, column 2. Row 3, column 2. So if I'm going to expand about a column, then I have to basically keep that column fixed and run through every single row. So yeah, 1, 2, 2, 2, 3, 2. Those are good. What do these matrices look like?
negative 1x, 3 negative.
-1x, 3, -4.
2 negative 2, 3 negative.
Okay. So we picked a column, we expanded by it. From that expansion, we identified the matrices that the minor matrices that I want. They are not enough though. What else do I need to do with them? What was that? Sorry. Okay, so I'm determinant of each one. So what is the determinant of minor 1, 2? Four minus 3x and 2, 2. -2. And then 3, 2 should be 2x minus 2. All right. Is there anything else I need to do? I need to find out the cofactors. I basically, now that I have the determinants, I need to figure out, are the values of those determinants good as is, or do I need to multiply them by -1? So what about the minor 1, 2? Right, because that's -1 to the 1 plus 2, -1 to the 2 plus 2, and -1 to the 3 plus 2. So odd power, -1. Even power, 1. Odd power, -1. So now I think I have everything I need to set up this determinant. So what is the determinant of A? So everything I did with M12, what's that going to contribute to the determinant? So we're going to multiply -1 by 4 minus 3x, right? So I'll call that 3x minus 4. Good. What am I missing? By x? How come? Right. So whatever the object, so whatever the, part of the matrix that I'm expanding on, what's in that column. So in general, what did I do here? I expanded on column 2. So I'm going to multiply A12 times cofactor 1, 2. Go menu. So what's the next piece of this? Minus -2 times 4. Okay, I see where the -2 comes from. That's the cofactor, essentially. I see where the 4 comes from. That's A22. Why am I subtracting? Okay, just making sure. So whenever we find all the things we need, we're essentially going to add together all these products. So this will be A22 times cofactor 22. And one last piece. So this will be 2 minus 2x. Okay. And that comes from A32 times cofactor 32. And since I wanted to find where this was going to be non-invertible, so I could find out what to avoid, I'm going to set that equal to 0. So questions on how we built up this determinant. Any different from how we set it up if we just have numbers in our matrix. So it should be exactly same approach. So now we're going to have a quadratic. 3x squared minus 4x minus 8 minus 2x squared plus 2x equals 0. Did I make something nice, the factors? Let's see. X squared minus 2x minus 8 equals 0. I think I did. So how does it factor? X minus 4, x plus 2 equals 0. So x equals negative 2 and 4. So essentially, this thing is invertible for any value of x I can come up with except for those two. How are we feeling? Cool. Questions so far? All right. Well, that was it. So I got one section left for you. Okay, so in this section, we're going to get a little deeper into determinants. So more properties of determinants. So to kind of ramp up to that, let's find this determinant here. So 5 by 5 now. How would I go about finding this determinant? Row 5, how come? It's all zeros. More zeros makes easier determinant. What happens if I expand on that row?
Just 0.
What's 0?
Determinant.
So you're saying the determinant of A is just 0. Are we okay with that? That's absolutely true. So think about what you would do if we kind of expanded. So, like we've said a few times now, when you're expanding my minors, doesn't matter which row or column you choose, you have 10 options here. If you do it correctly, they should all lead you to the same place. So you might as well choose the one that's the simplest. If I were to expand by row 5 here, then how would I find the determinant? Well, that would be, so the determinant of A would be A51 times cofactor 51 plus A52 times cofactor 52, so on. So those 5 terms, right? But what's true about all the A things in that summation? They're all 0, so I'm done. I don't care what the cofactors are. It's not going to matter. So if we have all zeros, those matrices always have, provided it's a square matrix, those matrices always have a determinant of 0. They have no inverse. Any questions on why that's true? Go ahead.
I had a separate question.
Yeah, go for it.
So,
Uh-huh.
do in non-square matrices have determinant?
No. So that's a good question. So a sort of a very related question is, can non-square matrices have inverses? So right. So the determinant is, it's very, very strongly connected to the idea of inverse. So there are many things the determinant of a matrix can tell you, and probably for us right now, the most important one is it can determine for you if a matrix has an inverse. So because of that, it really only makes sense to talk about determinants of square matrices. Because to have a determinant, I really have to have these two diagonals. the one that goes from the top left to the bottom right, and the one that goes from the top right to the bottom left. If I have a different number of rows and columns, I can't make either one of those. How are we doing? What if I change things a little bit? Is the determinant 0? Probably not. So what would I have to do here? Pick a column or a row. What would you like? Either column 1 or row 5. Smaller numbers are probably more manageable. So if I expand on row 1, or sorry, column 1, then what? So expansion by minors, column 1. If I do that, then that's going to basically reduce this, or I shouldn't use the word reduce because that already means something else for us. But that's going to yield another matrix, right? A smaller matrix. What's that smaller matrix going to be?
Negative 2, 4. 0, 5, 3, 2.
0, 5, 3, 2. 0, 0, 0, 11. Okay, what would I have to do from this matrix? So I can't take determinants directly off of a 4x4. Expand again. Where would you like to expand from? Column 1 again sounds good. If I do that, so again, expand by minors, column 1. What size matrix should that, or what order matrix should that give me? 3 by 3, what's that going to look like? Whoa, 5, okay, 5, 3.
5, 3, 2.
Okay. 0, 7, 8, 0, 0, 11. But now what? Okay, from where? Column 1 sounds good. If I do that, then I get 7, 8, 0, 11. Okay, can I deal with this thing? Okay, so how many determinants do I need? Well, let's find out. So now that we've expanded this thing 3 times, what can I do with all the things that I like kind of culled out of this? Cool. How do I do that? So yeah, so we work backwards to start with the smallest matrix we made. What do I do with that? Take the determinant of that. What is the determinant of this? $77. Is that my answer? Nope. But I need it. What do I have to do with that 77?
The cofactor.
Find the cofactor. Where's the cofactor going to come from?
3 by 3.
It's going to come from the 3 by 3, and specifically what entry of the 3 by 3? 1, 1. Okay. The first entries are always, or the top left entries are always positive, right? Okay, so I don't think I need to alter this 77. But let's kind of build up what we're doing here. So the determinant of A is equal to 77. And then the cofactor itself is 77 because I didn't have to, I just could multiply by 1. What else do I need? Multiply by 5, right? Why is that?
That's our A value.
What's that?
It's the A value for 1, 1.
Right. So for the matrix that we expanded from, so we expanded this matrix to get to this. So once we find this determinant, we have to multiply it by this, wherever the row and the column intersect, where we expanded that from. So that's 5. Okay, what's next? Multiply by 3 for basically the same reason. Now we're working backward to the original matrix. So where do we expand this from? From this 4 by 4. And 1, 1 is, entry 1, 1 is 3. And then what? Multiply by 2. Is that it? Okay. And just to recap, where did 77 come from? Right, so we multiplied 7 times 11, right? So in the end, we got 2 times 3 times 5 times 7 times 11 for our determinant. Which I'm going to leave it like that unless someone really wants to find out what that number is, but where do those 5 numbers come from? That's just the diagonal, right? So why did that happen? Are there times when we can just take the numbers along the diagonal and just multiply them all together? Go ahead. Oh, you're exactly right. So if you have a matrix that looks like that, so the first one we looked at, we had a row that was only zeros. That determinant is automatically 0. If A is upper triangular, then the determinant is the product of all of its diagonal entries. Why does that happen, though? So why did that happen here? Well, if we work back to like our smallest matrix, the fact that we had a 0 below the diagonal meant that it only matters what happens along the major diagonal. And then once you expand outward, that phenomenon carries everywhere else. These zeros here mean that anything that I would subtract from this product ends up being 0. So if we have an upper triangular matrix, we get to take a really significant shortcut with it. One question I want to ask here is, so I said if any row has only zeros, we know our determinant is equal to 0. Could I replace row with column here? Would that be true? I got 1 vote for yes. I got 1 vote for no. That's not what I wanted to do. They took for granted that one. So if I threw this matrix at you, how could we find its determinant? Go down column 1, which is all 0. So yeah, columns work too. Something else we talked about is this. If we transpose a matrix, it doesn't change its determinant. So if I transpose it, then I get 0, 0, 0, 1, 3, 5, 2, 4, 6. So essentially, if what you're looking at is determinants, then there really is no difference between rows and columns because the transpose has no effect on the determinant. So a couple of things you can take for granted. If you have an entire row of columns of zeros, or if you have an upper triangular matrix, you can take some pretty significant leaps. Questions on either one of those or why we can take them for granted? All right. Oh, yeah, I remember why I did this now. Okay, so let's find the determinant of this thing. It's not a trick, I promise. 2. How'd you get that?
2 times -2. Same.
2 times -2 minus 1 times -6. So +2. What if we swap the rows and do it again? So now let's find the determinant of 1, -2, 2, -6. What was that? -2. We agree? So swapping the rows had an effect. Didn't budget my space here. So the determinant of the rows flipped gave us -2. Let's triple one of the rows. Which one? Doesn't matter to me. Row 2 sounds good. So what's the determinant of 2, -6, 3, -6? +6. All right. Now let's do this. Replace row 2 with the sum of row 1 and row 2. So first of all, what would that matrix look like if I did that? Two, -6, 3, -4. Sorry, what? -8. Okay, that makes. What's the determinant of this? 2. So what did all this nonsense do? What did all these changes do to the determinant? So when I switched the rows, what happened? I got the opposite of determinant. What happens when I tripled one of the rows? Triple determinant. And I replaced a row with the sum of 2 rows. That didn't do anything, right? Is that a coincidence, or do you think that always happens? Let's replace row 2 with the sum of row 1 and let's multiply row 2 by something. Pick a number. 4 sounds good. So let's replace row 2 with the sum of row 1 and 4 row 2s. So 2, -6. What's this bottom row going to be? 6. -14. -8.
Yes.
So what happened that time? We quadrupled it. How come? So we quadrupled a row. Okay, so what are some generalities we can make here? So if I swap rows, you basically negate your determinant. If you multiply a row by k, well, then we basically multiply the determinant by k. So if you remember from the last section, one thing we said is that if I take the determinant of KA, then what does that do to the determinant of A? It multiplies it by K to the power of N. Because what do I really do if I multiply a matrix by a scalar? Multiply each component or multiply every single row. So if I'm multiplying every row by a K, then the determinant would be K times K times K. As many K's as there are rows multiplied by that determinant. If a multiple of a row is added to another, then the determinant remains the same. So I think I did something wrong because that's not what we saw, right? Did we add the multiple of a row to another? No, I did something slightly different. So let's do what that actually says. What if we take 4 of row A? So basically I replaced the wrong row. So what's that determinant? That one's 2. So if I add a multiple of a row to another row, then I did not change the determinant. The reason that we saw that determinant the first time we do it scale from 2 to 8 is because we multiplied a row by 4 and then left it as is. We left it there. So any questions on any of these shortcuts? Okay, so let's try to make use of them. I would like to find the determinant of this matrix. So, but instead of using expansion by minors, let's use Gaussian elimination. So what does Gaussian elimination do to a matrix? What form does it put it in? Upper triangular, right? So now we know something about the determinant of upper triangular matrices. We know that we can do something very simple with them. So if we can get this matrix to look upper triangular, we can get its determinant very quickly. It doesn't look that way right now. So what can we do to start trying to make this upper triangular? Go ahead. Add 2 of row 3 to row 1. Two of row 3 plus row 1. For upper triangular form? No. One, 10, -3. So no, I do not think that's not necessary to get it to upper triangular form, but I think what he did is going to make it more convenient going forward. We could have added some fraction of 7 to -3. Now we don't have to mess with stuff like that. Hopefully that didn't prejudice you too much on what I think should happen next. What should we do next? Go ahead.
We should add
So 3 of row 1 to row 3. So 1, 10, -3, 0, 3, -1, 0, 22. -9? Why do I feel so unconfident about that? Where? Which one?
22.
3 of row 1. What the heck did I do? Okay, so yeah, 3 times 10 plus 4. No, I did 3 times row 3.
Would -9 not be -11?
No excuse for that one. Okay. 3 times -3 is -9, plus -2 is -11. Okay. Now, okay, so we're one step closer to the thing we want. Now what? Go ahead.
Swap.
Row 2 and row 3 get swapped. How come?
Because if in our next step, if we multiply
We'll get 1 in the center. Oh, okay. That's what you're saying.
That's 11 times row 2, row 2.
Row 2 minus 11 row 3. Back to row 2. What does row 2 become? 0, 1, 1. Okay. Still not quite upper triangular, but I think we're in a way better place to make it happen. One more time, sorry.
3R2 minus R3.
Like that? Okay. So I think we're done reducing. Unless there's a mistake. Why wouldn't I have to make a mistake? I'm on a roll. That's what I thought. So you talked me out of it? Three times row 2 is 0 minus -1. I'm leaning towards 1. I feel like this is okay. So can we get the determinant now? What's the determinant? Is it 1? I believe the determinant of the thing we ended up with is 1. But what does that have to do with A? So let's think about this. the determinant of A, and then we did a bunch of transformations that modified the determinant, right? So let's think about what those did. The first thing we did is add a multiple of row 3 to row 1. How does that change the determinant? We added a multiple of one row to another row. It doesn't do anything. So our first move didn't alter the determinant. Second move, we added a multiple of row 1 to row 3. That also didn't change the determinant. We swapped two rows. Multiplied by what? Right. So that changes the sign of the determinant. This next one's a little tricky. We did row 2 minus 11 of row 3. And put that in row 2. What did that do to our determinant?
Multiplied by 11 or multiplied.
I think it remains the same because what we effectively did is this. Negative 11 R3 plus R2 back to R2. So what we essentially did is we added a multiple of row 3 to row 2. So I think that one even didn't make a change. Is that true for the very next one?
Yeah.
I see two steps in here.
Scale.
Yeah, so let me write this a couple ways. I'm going to factor the negative sign. Row 3 plus 3 row 2. Nope, minus 3 row 2. And we put that in R3. So I think we did two things here. We scale, it looks like we did not add a multiple of row 3, or sorry, what's the way to say this? So we put our result in row 3, but row 3 is not the row we scaled, right? Maybe it'd be more consistent if I wrote this in the same form as everything else. I think this is even still, like we added a multiple of row 2 to row 3 and put it back in row 3. Is that fair? But there's something else we did that we kind of did all in that one step as well. I think we multiplied by -1. So the determinant of A times all this stuff that came from our transformations equals the determinant of 1, 10, -3, 0, 1, 0, 0, 0, 1. Which we know how to take the determinant of matrices that look like that because they're upper triangular. So that's just 1, right? So we can kind of reverse engineer what the determinant of A is based on the effect of all those transformations. And I think in this case, the determinant of A is just 1, right? Questions? All right. What else? Oh, Oh yeah, last one. Then we're all experts and test ready. Four by four. Let's buy ourselves some more space. How should we approach this? Go ahead, Jack. Three times row one. Oh, so row two minus three row one. Back to R2.
Yes.
Okay. I'm going to rewrite that in a way that's going to hopefully make our lives easier at the end here. Negative three of row two, row one, plus row two, back to row two, right? So hopefully me writing it that way shows that I'm taking a multiple of some row and adding it to some other row and putting that result in that other row. Because doing that has what effect on my determinant? No effect. So good. So I think the way I wrote it down in a couple operations last time hid that fact. So 1, 3, 1, 4, 0, 0.
Yeah.
Nice. Minus 3 of row 1, 2, 3. Excellent. All right. Now what? That sounds good. Row 2, row 3 change. Okay, so we got a bunch of zeros under the 1.
Do
Okay, I'm going to rewrite that slightly. So minus 2 of row 2 plus row 4 back to row 4. And it's equivalent to what you said. But would you agree that I'm taking a multiple of some row, adding it to another row, and replacing that row with it? So what effect is that going to have on my determinant? I think that one's also for free. So 1, 3, 1, 4, 0, 2, 1, 1, 0, 0, 2, 3, 0, 0, 0. Oh, come on now. 1. All right, so now what? So the determinant of A is equal to what? I don't think it's going to be exactly equal to 4. Yeah, we had one row swap in there. So our first operation did nothing. Our second operation negated the determinant. The third operation was another row swap, or adding a multiple of a row to another row. Times the determinant of, I don't want to write this whole thing again, so I'll call this B. And the determinant of B is equal to 1 times 2 times 2 times 1. So -4. Which hopefully you'll agree that was better than dealing with all the minors you have to deal with. There's only 2 zeros in that matrix. I don't think there's a lot of shortcuts you can take with expanding that one. How we doing? Okay. That is all I have from you for the first 3 chapters. So that's basically, this is where the test content stops. So I heavily encourage you to go to that math.asu.edu /MAT242. I will put a link for that in this week's module on Canvas, but there's a wealth of past test questions and good things to practice on. Also in the textbook, the online, also an online, is it's a hardcover, but basically in the textbook, at the back of each section, there's a bunch of good problems too. If you go through a bunch of that stuff and you feel like you still need some stuff to polish up on, let me know and I'll find you some stuff. In the meantime, if you have questions, let me know. Otherwise, I'll give you 9 minutes back and I'll wish you a happy weekend.